what's going on here. I tried to copy this, and it's gone into a horrible mode here. I want to get out of here. Yes. Just turn it off. Would that do it? I can't. Oh, wait. Maybe this. No. That's good. No, I don't want to. Let's see. I think. Okay. Whoops. That's okay. Where am I? Here. Yeah. Okay. Good. Let me see if this is going to work. So I'm going to try it once more. Okay. Okay. We can get started now. Yes. Let me just move everything here. But it's not mirroring here. It's not seeing me. Oh, there it is. Okay. Okay, let's get started. So, short review of the bit we did on discrete time Markov chains. Let's note that we defined the important quantity, the one-step transition probabilities go from step I at time n minus 1 to step j at time n. It's going to appear in whatever we do. We define something called the first return to a state once you leave it. F sub j super n is probability. The first return is in n steps. Capital M sub j is the mean recurrence time. I see I forgot to use this word here. The mean recurrence time, once you leave it, on average, how long will it take to get back to that state? And we're going to use that quantity later to try to characterize states. And then this rather important quantity here, pi sub j of n, is the probability that at step n, you're in state j. And of course, that's a rather important quantity. It's going to tell us about number and system and where they are. And the example we chose to use was a simple one, a three-state system. And we'll be using this again and again. We're going to solve this system. It's simple enough and complex enough to be of importance. So, first thing I want to do is I pointed out last time that following this, there are two critical theorems about Markov chains. And they're quite important, so let's look at them and focus on them. I'm going to call the first one Theorem 1. I didn't turn on the mic. Now it's on. So here we go again. We're going to start with Theorem 1 for discrete time Markov chains. And it says the following. The states of an irreducible Markov chain what does irreducible mean? Go from any state to any other state. Okay. Are all either transient or all recurrent non-null or all recurrent null. Now, which of those three is the good case, the ones that's interesting that we can use properly? Yes. Recurrent? No. You keep getting there, and you get there in a finite time on average. Okay? And so that little example I showed you is an example of a Markov chain where all the states are recurrent. What's important is all the states are the same if it's an irreducible chain. So keep that in mind as well. And if periodic, they all have the same period. And that's the end of the theorem. So I'll put a little box here, if you will. But there's a bit more we can talk about. In our example, for example, if the hitchhiker wanders forever, he never gives up, never dies, he will pass through cities many times. Question is there a stationary probability of finding him in a particular city through all those journeys? So let's ask about that. And I'm going to define stationary in a minute. Is there a stationary probability distribution? And I'm going to call that probability distribution the set pi sub j, describing the probability of being in city J at some arbitrary time. But in particular, far in the future. Let him wander around for a long time. So this is going to be far in the future. Now, getting back to what we mean by stationary, a probability distribution is a stationary distribution and I'm going to name it capital Pj, for example, is a stationary if when we choose it for our initial distribution, namely what we're saying is pi sub j at time 0, super 0, is equal to this element in this distribution, capital Pj. So at time 0, we started off in this thing called a stationary distribution. Then, for all n, we will have that the probability P sub j super n is equal to capital Pj. In other words, if you start the system off in what we think is something called a stationary distribution, it'll stay there, which means the probabilities will not change. If you start off in one of those cities, say in Zeus, say with probability a quarter, if it's a stationary distribution, At every step, the probability of being in state city 1 is also a quarter. And by the way, a quarter is not the right answer, but whatever, we're going to calculate it in a moment. But that's what it means. So it's a very powerful distribution. And it turns out that finding this quantity, capital P sub j, in the limit is the most important part of Markov chain analysis. We seek to do that all the time. We'll give you some state description, such as the example. What's the probability of a state I at time n in equilibrium? So you can talk about, in the long run, the fraction of time you're in that state, and that's a value in our analysis. Now, this question is answered in this next theorem. So this is theorem 2 now coming up. In an irreducible and aperiodic, we're adding that now, homogeneous, we've implied that before, I want to be explicit here, Markov chain, the limiting probabilities what do I mean by that? I mean pi j, which is the limit as n goes to infinity, of pi sub j super n. That if you let this thing run, and the probability of being state j as n gets large, this limiting probability pi j always exists and is independent of the initial state distribution. Boy, that's powerful. So let's say that. And we're going to give some very nice example of this shortly. But there's more to it. Moreover, either case A, all states are transient, or all states are recurrent null, in which case this limiting distribution is not too interesting. Namely, it's 0 for all j. And there exists no stationary distribution. This is the bad case. These two cases are bad. You don't like them. It never settles down, or it runs off somehow. Or B, all states are recurrent null null. The good states. in which case we do get a solution. So in which case pi j is greater than 0 for all j. Furthermore, in which case the set pi j is a stationary probability distribution. And moreover, that solution, those pi j's, are equal to 1 over the mean recurrence time for each state. It doesn't mean the mean recurrence time is easy to find. We're going to find the pi j's other ways. But it has that property. Furthermore, in this case, the pi j are uniquely determined following equations. So first of all, the fact that the sum of all those probabilities must go to 1. That's no surprise. And 2, the pi j itself is related to the other pi's through a sum, namely pi I pij. Over all I. Now I want to label these equations, this summation as equation 3 and this other equation 4. So this equation 4 is telling you how you can calculate them. If you know the state description, you know the PIJs, probably going from one city to another in one step. So you're given the PIJs typically, and that equation, if you could easily solve it, will give you the equilibrium distributions, pi j. Now notice there's a very important word here which may or may not slip your mind. Uniquely determined. There's only one solution. And if you can find it, you got it. So I'm giving you a little hint now. If you have a complex Markov chain, and you're trying to find the pi j's, the equilibrium distribution, if you can guess it, you can check your guess by plugging it into that equation to see if it solves it. Now, sometimes you can and sometimes you can't. It's a very powerful approach, though. There's only one solution, and it's unique. And it's a stationary distribution, which means if you start the system off with those probabilities, namely with probability pi j, you start off in probability in node j. At every step along the way, those same probabilities will hold. Pi j super n will always be pi j. But you don't have to start off there. You can start off with an arbitrary distribution, and it'll bang, bang, bing, 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 and settle in to that stationary distribution given by equations 3 and 4. Now, while we're at it, I'm going to introduce a little bit of notation, but that's the end of the theorem, by the way. I'm going to use a vector notation, pi with the bar below it. I think I've talked about that before. The bar below indicates a vector, to be that set of solutions. It's the vector containing pi 0, pi 1, through the whole set, however many states there are. And if we define capital P to be the matrix of PIJs, it's a square matrix, Then equation 4 says that pi, the vector, equals itself, it's a row vector, times the matrix P. And that's a very important equation. We're going to show this over and over again. We're going to use it. Now, any questions about these two theorems? They're really critical to Markov chains. They're very powerful. They're very intuitive. And they give you some real tools to solving these systems. Okay. Now, there's another concept related to all of this called ergodicity. You may or may not have heard of ergodic systems. Anybody who studied communication theory knows about ergodic systems. For example, in that field, if you have an ergodic stochastic process and you let it run for a long time, there's a time average over time for the value of that process. Also, if you let one of those run for a long time, you can have many duplicates of that. Different numbers, they're each probabilistic. You let a whole series of these things run using the same stochastic process. That collection of traces is called an ensemble of the stochastic process. The ergodic theorem says that the time average is equal to the ensemble average. If I take a slice at any time with a large number of these sample functions, the average here will be the same as the average here. So there's something sort of nice about ergodic process. We're not going to take advantage of that here, but for those who study communication theory, that's very important for time series. Okay. So let's do this a little more formally now. A state, EJ, is ergodic if it's an aperiodic recurrent non-null state, and by that I mean, i.e., if fj equals 1, that means the probability of ever returning is 1, and the average recurrent time is less than infinity, and gamma, the period, is equal to 1. So that's just using definitions we talked about last time. So I'm talking about such a state. If all states of a Markov chain are ergodic, as I just defined, then the Markov chain is said to be ergodic. Moreover, a Markov chain is ergodic if the set of probabilities, pi j of n, as a function of n always converges to a limiting distribution. Limiting stationary distribution. And we've called that pi j, the set of probabilities pi j. Independent of the initial states. All states of a finite aperiodic irreducible Markov chain no surprise, are ergodic. Again, moreover, an irreducible aperiodic Markov chain. And by the way, you don't have to suffer writing all this down. It's all in the book. But maybe writing helps you. That's why I'm doing it for you here. Irreducible aperiodic Markov chain is ergodic. If equations 4 has a non-null solution, for which, for which the sum of those probabilities in absolute value, and of course they're all positive when we find them, is less than infinity, it's finite. Now just make a note, these probabilities we're talking about, they're called the equilibrium probabilities, which means if you start with it, it's stationary, it stays there. Okay, so having done all of this, I want to now go back to our example. This is the example we've been using. And again, we have this transition probability matrix, capital P, which we'll write down in a moment. And we've got the equilibrium vector we're looking for, pi. And the equation we're going to use to find it is pi equals pi p. That's the process. I'm just reminding you what we're going to do. So in the example, what is capital P? What's the probability of going from state 0 to state 0? 0. What's the probability going from state 0 to state 1? 3/4. And from state 0 to state 2 is 1/4. Probably going from state 1 to state 0 is 1/4, looking at the diagram. From state 1 to state 1 is 0. From state 1 to state 2 is 3/4. And from state 0 to state 2 is 1/4. And 1/4 from 2 to 1, and from 0 to 1, from 0 to 2, 0 to 0, 0 to 1, and 2 to 2 is 1/2. let me say that last one again because I mumbled it. This last row is probably going from state 2 to state 0. That's this link here. From state 2 to state 1 is this quarter here. And from state 2 to itself is a half. Okay, so it's a very simple system. Notice the rows always sum to 1 by definition. When unit state, there's someplace else you have to go, including yourself. Okay, so let me just point out rows sum to 1. And by the way, this is finite, it's irreducible, and it's aperiodic, so guess what? It's ergodic. Most of what we're going to deal with will be ergodic. Okay, now let's let's solve the equations pi equals pi p. Let's actually do the work, okay? So the first equation will be, take this vector pi, let me write it out here. Pi 0, pi 1, pi 2, into the matrix. So I'll get pi 0, left-hand side of this equation, is equal to that first row times the first column. So it'll be basically 0 times pi 0 plus a quarter times pi 1 plus a quarter times pi 2. The second row will give me that pi 1 is equal to 3/4 pi 0 plus 0 pi 1 plus 1/4 pi 2. And the third one will give me pi 2 is equal to 1/4 pi 0. I'm going down these columns. Plus 3/4 pi 1 plus a half pi 2. Now, if you look at these equations, you will note, and you should find, that minus a is equal to b plus c. Namely, there's a dependency among the three equations, and there always will be. There always will be. These are not three independent equations. If it's k states, you've got k minus 1 independent equations. So what's the extra equation? Namely, that the summation of the pi's is equal to 1. Now, you can go and solve these equations. It's not complicated. The answer is the following. Pi 0 equals 1/5, which I'm going to write as 0.2, as you'll see why in a moment. Pi 1 is equal to 7/25. That's 0.28. And pi 2 is equal to 13/25, which is equal to 0.52. First of all, let's point out this is the equilibrium solution as we claimed. And we're going to go into some more details how we got this in just a moment, but that was simply solving these equations, 2 of the a and b plus this last summation of pi equals 1. Now this is the equilibrium solution. It's what happens after a long time. It's a stationary distribution. But what about starting in one state and watching this thing evolve? Supposing you don't start with the equilibrium distribution, okay? So namely, I'm going to ask about, how about the transient solution as a function of n? How do those probabilities move? Namely, you want to go from n equals 0 to 1 to 2, all the way out to equilibrium. So I'm looking for pi sub j super n. So again, the probability of finding the hitchhike, I'll abbreviate that HH, in city J at time n, or step n, as you like. I'm going to write a vector of these probabilities. I'm going to call it pi subvector super n, and that's defined as the vector containing these separate ones, namely, it's pi 0 at time n, comma, pi 1 at time n, etc. All of this is at time n. Now, if you're given capital P, the transition matrix, how do you get that? You just look at the diagram. We wrote it down here. You get it right from the state diagram. Given P and an initial state probability, say pi vector at time 0, pi 0, pi 1, pi 2 at time 0, we see the following, that the vector of probabilities at time 1 must be equal to the vector at time 0 times P. You start off with some initial vector, you take one step. So you move through the transition matrix. Following that, pi 2 must similarly be pi 1, where you were a step ago, times P. But we know what pi 1 is, so that's pi of 0 times P squared. And basically, that's going to take us to the obvious equation that pi super n as a vector is equal to where you started at time 0 times p to the n. We also have come up with a similar intermediate step, which was pi super n is equal to one step earlier, pi n minus 1 times p. Both of those are equations you should take note of. These are separately important equations. And of course, all of that is for n equals 1, 2, etc. Okay, so now we basically generated those two equations. Now we know that the stationary pi that we're looking for, it comes from taking the limit of what we had before, so that pi itself is the limit of pi n as n goes to infinity. If it's irreducible, aperiodic, homogeneous Markov chain, the limit will exist. Theorem 2 told us that. Okay. Yes? Yes? No. Why do you? The question was, am I implying from these equations that when you're in a state, you stay in that state forever? The answer is no. I'm not sure why you're asking that question. I mean, if I was in some state, say, Zeus, why does that equation suggest I'm going to stay there? In fact, we know we don't. Well, why do you think the equations on this page suggest that? You're looking at this equation here? This one? It says you start out somewhere and you transition n times. That's why it's p to the n. Every time you go through the p matrix, you've taken another step. With what probabilities? With the Pij probabilities. Yes, John.
I think that P doesn't show I, J, that's fine. And things like that. So every time you get a different probability, even though it says P.
No, P is this constant matrix. You don't get a change. This matrix.
Every time you move from one state to another state, you get the particular part of the, like, for example, alpha to another state, you get 3 divided by 4. In the next step, you might get 1 divided 4.
Oh yes, you're moving. The point is you're moving around in this state diagram. So if you've gone from Zeus to Sukh Samad, the probabilities you face there are different simply because you've moved to a different row in this matrix. When you start off with, say at Zeus, you're in state 1, you're going to see these probabilities. If you move to state 2 next, you'll see these probabilities. So it does change. But the probability expressions, what we said down here. What's going on here? How do I get rid of that? No. Oh, there it is. Thanks. Okay. Another question, yes? Yeah. In 2 steps, that's correct. The p squared is where you go from in 2 steps. It's the probability.
P squared 0, 0. So let's say like P squared 1, 2, for example, would be the probability of going from state 1 to state 2 in 2 steps.
That's correct.
And in the example that you had, the only way to do that is go from 1 to 2 and then in the next step state 2.
Each example is different, but it doesn't contradict what we're saying here. I'm not sure what's troubling you.
I was trying to understand like what the P to the N matrix would imply, like any one entry of the P to the N.
It's the probability of going from a particular I to some other J in n steps. And it's the P to the N. You multiply the matrix out by itself n times. Exactly. It'll carry all the paths. Exactly right.
Like there's like in this example, like you go from 1 to 2 in 2 steps, there's only one way. You go from 1 to 2, and the next step you stay in 2 to 2. But in another hypothetical example, there was like more than one way to go from state 1 to state 2.
No, there's more than one way to go from 1 to 2. You can go to 0 to 2, or you can go to 2 and back to 2.
Oh, so then the P12 of P squared takes into account all those.
All of them.
So it's like a sum, like you individually added them up, you get that same number.
You'd have it includes all the possible paths. Exactly right. Okay. Now, one other way to get the simple equation we want is the following. I'm going to number these equations here. I'm going to go this equation 6 and this equation's the other way around. I'm sorry. For my purpose, I wrote them backwards, so I'm going to write them down, 7 and 6. Because I want to refer to this equation. So from equation 6, which is pi n equals pi n minus 1 times p, if we take the limit as n goes to infinity for that expression of pi n, that would be the limit on the right-hand side as n goes to infinity of pi n minus 1 times p. And what does that give us? That gives us pi, the limit on n, is equal to the limit of pi n minus 1, which is the same thing, pi, times our matrix P. So there we are again. We keep coming up against this equation, which in fact will allow us to find the equilibrium solution. And notice it's independent of the initial state distribution, independent of pi 0. Okay, now what I want to do is I want to track this transient. I want to actually, for the example. And we can consider 3 extreme cases. Case 1, for sure you start in state 0. Case 2, for sure you start in state 1. Case 3, for sure you start in state 2. And let's watch it move around in those 3 cases. Okay? So the first thing I'm going to look at is where the initial state probability, pi super 0, as a vector, is equal to 1, 0, 0. For sure we start in state 0. So after one step, it will be pi of 0 times p, which simply be vector 1, 0, 0 times the p matrix, which is our friend 0, 3/4, 1/4, 1/4, 0, 3/4, and 1/4, 1/4, 1/2. Okay, can somebody tell me what that is? Exactly, 0, 3/4, 1/4. If you look back at the example, it's obvious. If you start at state 0, where you're going to be next? 3/4 of the time in state 1, 1/4 of the time in state 2. And that's what that's telling me. Now if you do it again, pi super 2, having started there, will now be this initial state vector, 0, 3/4. We're starting in the 3/4, 1/4 case. We've moved one step in, times again that matrix 3, 0, 3/4, 1/4, 1/4, 0, 3/4, 1/4, 1/4, 1/2. What's that equal to? It's 0 times 3/4. Yeah, it's one step, right. This is the second step. Into state 2. So 0 times 1/4, 3/4 times 3/4, 1/4 times 1/2, which means we get 1/4, 1/16, and 4/16. Now I'm not going to torture you all the way here. I'm going to show you what happens when we get all of this done. Let me pull up a picture that's in the book. And that is Come on. Oh, I've got the, you can't see it, but I got the circle of death again. I may have to abort this thing. Saved by the bell. I'll work it out while you're on break. Thank you. problem more or less solved until we hit it again. Okay, so what we've been doing here is we've been trying to watch the transient starting in this particular state, namely state 0. And I'm showing you a table here of what happens. For sure, we're starting in state 0 with probability 1. After one step, we saw 0, 3/4, a quarter. Then we just saw this one. And if you keep going, in the limit, you're going to get here. Now, guess what that is? What's the name for that distribution? Stationary distribution, equilibrium distribution, etc. That's what we're looking to find. But notice, in just 4 steps, we're almost there. It's converging rather quickly. And we'll talk about that in just a moment. Now, I'm going to show you what happens if we start it in different states, if I don't mess this up again. So far, so good. Come on. Terrific. What I'm showing you here is 3 cases. The one above, the one I just showed you for starting state 0, is this table here. This next table starts in state 1, and this last table starts in state 2. And you notice they all end up, as they should, with the same equilibrium distribution. It shouldn't matter which one you started in, according to the theorem. And here you can see, that's on page 33 of the book if you want to look at it. It gets there pretty quickly. By the time you're through 4 iterations, you're pretty much there. That's just an observation. It doesn't, give you any great success. But I'd like to describe that in another way. And in one of your homework problems coming up, I ask you to do the following. I ask you to consider something called barycentric coordinates, namely this thing. Oops. I ask you to consider an equilateral triangle, as I've drawn here, of height 1. And we're trying to represent probability vectors. In this case, the vector has what length? 3. So we're going to represent it in 2 dimensions using a 2-dimensional simplex, which in case of 2 dimensions is an equilateral triangle. In case of 3 dimensions, it's a simplex. It's basically a tetrahedron of height 1, etc. And they're called barycentric coordinates, some term you'll probably never use again. It comes up in information theory quite a bit, by the way. And it has the following property. If I set the height equal to 1, and this is an equilateral triangle, then any point such as this is such that the perpendicular distances to the 3 sides adds up to the height, which in this case is 1, which means that those 3 red lines I just drew represent the probability of a vector having length this much, and this much adding up to 1. So I can represent any, in this case, 2-dimensional simplex, 3-dimensional probability vector. Any place in or on this triangle is a possible set of numbers representing 3 probabilities. So, for example, if I started at, let's see, up here we began at state 1, 0, 0. if I started here and I went one step into this chain, I'd end up with the numbers we got just a moment ago, namely these numbers here. Now I'm going to show you that process as we go along. You're going to prove for homework that the sum of those three perpendiculars is equal to the height of the equilateral triangle. Not hard to do. Just make you play with it a little bit. But I want to show you how that works in this particular example. And that picture is again in the book. I'm going to copy it here. This is that same triangle, but for this example we've been running here. What I want you to notice is the following. If I start in, oh, by the way, the other thing I didn't say about this triangle once I put it, the distance from what I call side 0, how far you're away from that, say I'm over here, the perpendicular drop is p sub 0. It's pi sub 0. And this would be pi sub 1 for side 1, and this would be pi sub 2 for side 2. So if I sit right here, the distance is how much? It's 1. And distance 0 to these two other axes. So this does represent the initial state, 1, 0, 0. Now if we take that first step in, it turns out that, and I'm looking at the triangle now to remind me, I go to this point after one step. Namely, it's a quarter, 3/4. And 0 for state 0. Remember the answer was 0, quarter, 3/4. And after one more step, if you go through the calculation in that table, I go from here to here. Similarly, if I started in the third state, I start from here. The first move would be to this point, second move to this point, and alternatively, I started in state 1. The first move would have taken me here, second move would have taken me here. Okay. So let's consider the three extreme cases. Let's simultaneously think I could have started in state 0 for sure, state 1 for sure, or state 2 for sure, and take one step in. Now before I start, where can I start? I can start anywhere in this triangle. I choose to start here. If I consider starting in any one of these corners and go one step in, I'm going to end up with this as the first step from one corner, this from another, and this from the third. Which means, and I'm going to draw this now with a color, that means a triangle from here to here, among those three first steps. This triangle I just drew contains an area, that skinny little triangle. That's the only place you can be after one step, no matter where you begin, because I consider all three extremes. After one step, you have to be inside that red triangle. And after two steps, I'll have, this is a two-step, this is a two-step, and what am I missing? Yeah, this is the other two-step. So after two steps, I'm stuck in this little blue triangle, no matter where I began. Now already after two steps, I'm contained to a very narrow space in this probability space. Now if you keep going to get to that convergence, which was this point, whoops, I don't want to draw that in this way, 0.2, 0.28, 0.52, that's where this arrow is pointing. And I'll use another color now, say green. You're going to end up right there, no matter where you began after a lot of steps. That is the equilibrium distribution. It was those three values, 0.2, 0.28, and 0.52. Now, I'm showing you this just to give you a sense as to how quickly you move in there. Now, the rate at which those triangles shrink is related, believe it or not, to the eigenvalues of that P matrix. Just a comment. You know, we're not proving that. You'll see that later if we study some matrix theory. Okay, so I want you to understand exactly what's happening here. Now, what happened? Okay. So basically, I want to make the point that it converges quickly. And again, I show you that triangle to give you some sense as to what's going on here. How quickly these Markov chains converge to their limit, depending upon the probability transition matrix. So I want to make the point, I'm going to say it converges quickly. But now I want to look for the limit. Look for the explicit solution for Pn. Now, why do I want to do that? Because a few minutes ago I showed you those equations 6 and 7. One of them said this. It said that pi super n as a vector is equal to pi super n minus 1 write this more clearly times p. Now that you can do. If you want to find pi super 152, you'd have to do this 152 times. Whereas the other equation we had, which says you want to find pi super n, is equal to the initial state probability, which you have, times p to the n. So if I knew p to the n explicitly, I could find pi super n with one calculation. So our challenge is to find p super n. Everybody understand why that's of interest? It's a more direct solution for finding the transient solution at any value of n. Okay. Now if we look at this equation, what kind of an equation is that? Is it a difference equation? You bet. It happens to be a vector difference equation, or if you will, a matrix difference equation. But it's in a matrix, it is a matrix difference equation, I want to say so, because we know something about difference equations. And I want to use it to find p super n, okay? So somehow, if I want to find pi n, I want to define a z transform for pi super n. So let's think about what we used to do. If I have a function of an index n, if I multiply by z to the n, and sum over all values, in this case n equals 0 to infinity, that's a z transform for this vector. And I'm going to give it a name. I'm going to use 3 lines to represent it's a vector, even with the underline. That is defined to be the z transform of the vector pi super n. It's beginning to look like something we can deal with. And this, of course, will exist in the unit disk for absolute value of z less than or equal to 1, because we're dealing with probabilities. Okay, now, a couple of days ago, if I told you you have a difference equation, how do you solve it? What are the steps you take? What's the first step? Here's the equation I'm after. That's a difference equation. What do you do to it? Anybody. You did this in homework a few times. Yes. Tag it with z, which means multiply everything in that equation by z to the n. So let's start with that, okay? On the left-hand side, I got pi super n, multiply it by z to the n. On the right-hand side, I'll leave a little space here. I've got pi super n minus 1 z to the n times p. P is not a function of n. Next step, after you multiply by z to the n, what do? Sum. So let's sum it over all possible values. Now, this equation that I've marked up here, it's a matrix difference equation, that's good for what values of n? N equals 1, 2, etc. I don't know what pi sub minus 1 is. So it's only defined for n equals 1 on. So I'm going to sum over the range from 1 to infinity, and same on this side. Okay, now what's the next thing you do? In this equation, you look for the z transform that we just defined up here. Oh, I left out the z. I'm sorry, I should have put the z in here. You look for this function. Well, on the left-hand side, do I have it? Left-hand side looks like pi of z, doesn't it? But, excuse me, I'm missing the 0th term because the definition is from 0 and I'm starting with 1. So let's put it in and take it away in the usual way. Namely, the left-hand side is this guy I'm looking for, pi of z, minus the first term, which is pi super 0 times z to the 0, which is 1. Now on the right-hand side, what do I have? Well, take a factor of z outside. What's left is pi of z. All of that times p. Next step. Find a simple expression from that for the z transform. Let me do a little bit of algebra, okay? But I need matrix algebra, not linear algebra, okay? Not ordinary algebra. So I need to define, basically, a matrix inverse. So what I'm going to get is, on the left-hand side, I get pi of z times the identity matrix, that'll give me pi of z, minus z times p, basically, but I'm taking the inverse of it. So pull it on the left-hand side. What's left on the right-hand side? Just pi of 0, right? And now I want to solve for pi of z, which means now take the inverse of that thing I have. Multiply both sides by I minus zp inverse. So I get a 1 on the right-hand side, an identity. On the right-hand side, I get pi super 0 times quantity I minus zp inverse, matrix inverse. Now we also know something else, that pi of z, this z transform I have, has as its inverse what function? What is the inverse of the pi of z? We look at what's the definition here. What's the inverse here? It's pi super n, right? So we know that. And we also know that pi super n is equal to pi super 0 p to the n. If I look at these last three equations, that tells me immediately that I minus zp inverse is the z transform of what I'm looking for, of p to the n. I'm going to take this definition of pi of z, and I'm going to call this thing equation 8. Because the thing I just cooked up now, I'm going to call equation 9. So now we have an expression on the left-hand side whose inverse transform is what we're looking for, p to the n. Now, it's not always easy to form the inverse I minus zp. So let's do it for our little example. For our example. Now let me copy the example and the P matrix again. Don't need this. Let me just move this over here. Okay, let's do it for this example. So let's write down what I minus zp looks like. Not the inverse, but the thing itself. Well, certainly I'm going to get a 1 down the main diagonal. I'm going to get a 1 here, a 1 here, and a 1 here. And from each of the elements in this matrix, I'm going to take minus z times p. So in this position here, minus z times 0, which is 0, fine. In this next position here, I'm going to get minus z times 3/4. So that becomes minus 3/4 z. And similarly, minus 1/4 z in this term here. To fill the rest in, it's again another minus 1/4 z. But now, this is a 1. This 1 on the right here is minus 3/4 z. In the low second row, I get minus 1/4 z, minus 1/4 z, and now I'm going to get a 1 minus 1/2 z. Okay, now I need its inverse. Now how do you form a matrix inverse? Yuck. Pain in the neck. But one thing you do need is the determinant. So let's form the determinant. Okay, it's going to basically take, well, you can write it out if you remember it. If you write out what's taking you through all the pain, you're going to end up with the following expression. 1 minus z over 2 minus 7/16 z squared minus 1/16 z cubed. If you look at that, you see the roots of this? You see any root of it? Are you good at finding roots? The simplest one to try, as always, is z equals 1. Now, what do you know? It's a root. You'll always have such a root, okay? So let's write it out, okay? It's 1 minus z, and the rest happens to be 1 plus a quarter z squared. Which means now we have to form the inverse. And that's a task I wish for no one. Even in 3 by 3, you're going to make an error, for sure. So either use a computer or a calculator, or you look in the book, okay? And I've already done this one, so let me pull it up. This baby right here. And it's in the book, as I said. What is happening here? That happens to be the inverse. It's doable, and you're going to make algebraic errors for sure, okay? But now, what's our next job? What is the inverse of this, the Z transform inverse of this thing? I told you a moment ago. Why are we even looking at it? Because it's going to give us p to the n, right? And that was the whole object here. So we have to find the Z inverse of this guy. Now it turns out you can already see this denominator is giving you the roots on which we're going to do a partial fraction expansion. And the rest of this is giving some interesting stuff. It's given us, we got polynomials here, second order polynomials. Now if you remember your homework, if you have z times g of z, what is the inverse? It's the inverse of g, say g sub n, and the z does what? Gives you a factor of n. It's in the table. So what I want to do is I want to pull out all the constants in this thing, things that don't depend upon z, put them in one matrix. I want to pull all the guys which have 1 power of z, etc., throughout here, put them in a second matrix, and all of them have a second power of z into a third matrix. Because each of those, I can use that little trick. Z to a power times a function of z has an inverse, which is the inverse of the function of z, times some function of n plus 1, etc. So let's do that. I'm going to rewrite this thing now. The thing I'm trying to invert as something over a big determinant. And I'll write that down here. And that determinant is the thing that we just had upstairs. It's this baby here. I'll just copy it. And upstairs, I'm going to get 3 matrices. And let's do that. First, the one with only constants. So and what is that matrix going to be? It's simply the identity matrix. 1, 1, 1, and all the rest are zeros. That's part of the matrix I show on the top of the page. Plus, I'm going to get z times another matrix. And what are the coefficients of that? Well, let's pull it out. The 0, 0th term is minus a half. The next term is right here. It's 3/4. Next term is right here. It's 1/4. And the rest of it goes as follows. You can just see it from the picture. It's 1/4. It's minus a half. It's 3/4. Next is 1/4. 1/4, and 0, plus z squared times another big matrix. I'm going to move this over a little bit. I can do that and you can't. And all of the z squared terms, which is minus 3/16, minus 5/16, and 9/16, etc. Next row is 1/16, minus a 16th, and 1/16. And the last is 1/16 again, 3/16, and minus 3/16. Okay, now, next step is the partial fraction expansion. How does the partial fraction expansion work? Suppose I want to basically find what deals with this root. Remember what you do? You multiply by that root and evaluate everything else at z equal to the root, at z equals 1. So you have z equal to 1 upstairs here, and z equal to 1 here, and you calculate that. That's the way you do partial fraction. So let's do that, okay? So this whole thing is equal to 1/1 minus z times that thing I just cooked up. And downstairs, what will I get before I go on any further? When z equals 1, I get 1 minus 1/4 squared. Okay, that's 25/16. And upstairs, what do I get? When you set z equal to 1, this upper left term will be 1 minus 1/2 minus 3/16. But what I want to do now is multiply everything by 16. So I'm going to get rid of this 16 down here just for convenience. I'm going to take that out and multiply everything upstairs by 16. When you do that, if you do the arithmetic, you find out that this turns out to be 5, 7, 13. And that's true for each of these rows. Plus some other terms. And now let's find all of those terms. And if I'm not mistaken, I've copied that from the book. And it's right here. I'm getting good at this now. When I do that for all the other terms, the double root and the single root, I just gave you this one here. Here's what we get. Now, let's look at this. First of all, each of these rows sums to 1. Each of the rows here and here, the rows sum to 0. So these rows for which they sum to 0, it's called a differential matrix. Now there's something very telling here. I know that when I invert the 1 minus z, that'll give me a function of time which doesn't change. It'll be 1 to the n. So whatever this whole thing inverts to, it's going to remain constant for every n. What does that suggest? That this is the stationary solution. And if you look at these guys, they're going to get something like, well, this one down here, this one, I'm going to get minus a quarter to the n. And that's going to go to 0 as n gets large. And this is going to give me sort of an n times a quarter to the n. It too will go to 0. So these guys here are going to disappear as n gets large. That's part of the transient solution. So I'm looking at the stationary solution here and the elements of the transient solution here when added to this. Okay? So the next step is, let's invert this by inspection. Our old homework friend, okay? Turns out there are matrices that instead of constants. No problem. Okay, well, I've done that in the book. And let me show it to you here. When I invert, remember the inversion of this matrix here, this Z transform, is in fact p to the n, that which I was looking for. So the solution for p to the nth power is given by this expression. And once again, just to remind you, this basically is the equilibrium solution. Remember what it was. Remember, the example we used, the equilibrium solution was 0.2, 0.28, and 0.52, which, by the way, happens to be, in fractions, 5/25, 7/25, and 13/25. And you can see it in this matrix I'm pointing to. This whole expression I've just written out is the transient solution. And it took some matrix inversion, but the idea is there. And so now, because we know that to find the thing we're really after, the equilibrium, the time-dependent probabilities of each state, that's equal to something I know, the initial state, you give that to me, times something else I now know, p to the n. Boom, done. That's your transient solution. It's all there. And if you want to try that, let's try this, for example, for n equals 0. Okay? For n equals 0, what do I get? I'm going to get 5. I'm going to get basically a fifth times 0. And then I'm going to get 1/25 times 20. So I'm going to get 5/25 plus 1/5 times 0 plus 20/25, which equals 1. Namely, I'm getting the identity matrix as I should. Namely, pi super 0 equals pi super 0, p to the n, but n is 0. So it's basically an identity matrix. And that's what I should get. I'm getting back pi to 0. And you want to try for n equals 1, you get the same thing, etc. Now, I made a comment before about how quickly these things go down. Let me tell you right now. The transients, these transients you're looking at here, this and this, those transients decay at a rate of 1 over the zeros of the determinant. Which in our case is 1 over 4 times 4, 1 times that. The 1 is the 1 minus e. Each of the others has a root of 4, namely at a rate of 1/16. So that's the rate at which the triangles shrink. They shrink by a factor of a 16th every time you take a step. And that earlier picture I showed you up here of these triangles shrinking down to a small piece, from black to red to blue, finally to the green point, they're shrinking by a factor of 16 each time, because that's the product of the roots. And those are the eigenvalues. Those roots are the eigenvalues. Okay. So we've now shown how to find p to the n. Now, we'd like to take a little excursion and start to prove the following. I'm basically done with the computation of pi super n, in particular, the limit of that, namely pi, which is most of the work we have to do with Markov chains in queuing theory. But I did tell you that Markov processes imply that the time in state is exponential, and if they're Markov chain, the time in state is geometric. And I'd like to basically prove it for the discrete time. So let's take a small excursion here. I want to prove that the time in state is memoryless. By memoryless, I mean when you're going to leave that state doesn't depend about how long you've been there. There's no memory about how long you've been there. And in this case, for discrete, it's going to be a geometric distribution. And that's the geometric is the unique memoryless discrete distribution. Okay? Let's assume we just entered state EI. Now, the system will remain in EI at the next step with what probability? Think of Pij, tells you what the transition probabilities are. With what, if you go into state I, what's the probability the next step you're still there? What is the P matrix? Contains elements Pij. Probably going from state I to state j in one step. So if you're going to state I to state I, what's the p associated, little p associated with that? Pii, of course. Okay. It will leave the next step with probability 1 minus Pii. It can go anywhere else except itself. Of course, if it ended up staying there, it's going to stay there again with what probability? Pii. Okay? So the probability that you remain in state EI exactly m steps given that you just entered this state, what's the probability you basically spend there exactly m steps? Anybody? Stay there once, PII. Stay there twice, 2 in a row, PII squared. M times PII to the m. Then you got to leave. 1 minus PII. Okay? So that's PII to the m, and then for sure you got to leave. Well, son of a gun, that's a geometric distribution, isn't it? Now, by the way, the book goes into the non-homogeneous case as well. I'll let you play with that yourself. Okay? Similar argument can be used for the continuous time, the exponential. Okay, now I'm going to introduce a subject just to get it started before we end the class, and it's the following. Something I talked about at the very beginning of the first lecture. I talked about an arbitrary system. I called it a flow system. Namely, something's flowing into this system. And stuff leaves that system. So there's a flow in and a flow out. And to make this rather explicit, I'm going to talk about the thing that's coming in are gallons of water. Okay? So suppose they're coming in at so many gallons per second, and they're leaving at so many gallons per second, and inside the Don system, there's so many gallons that it's stuck with. And I'm going to let the symbol F sub S of T mean how many gallons are in the system S at time T. And let's talk about the rate at which things are coming in. Namely, let little f sub I of t be the rate at which gallons flow in, and little f sub 0 of t be the rate at which gallons leave. Well, it's pretty clear that the amount in there at time t is equal to the integral, suppose we start with 0, up to time t of all the stuff that flowed in, namely f sub I of, I'll call it x dx, minus the stuff that flowed out over the same interval from 0 to t, f sub O of x dx. And you can draw that in a picture if you like. I think yeah. The reason I'm showing you this picture is I want to talk about rates of flow in and out of a system, and the system I'm going to talk about will be the states of the Markov chain. And instead of gallons, what will I be talking about? What flows in and out of states of a Markov chain? It's a little tricky question. Probabilities. If you look back at our system earlier, where is it now? Our good friend here. If I'm in state 1, there's a probability 3/4 of what was here that's flowing to state 2. and there's a probability of 1/4 of whatever 0 had flowing at state 2, plus half of what he had keeps flowing back. So we're going to talk about probability flowing around in these states. Isn't that what I talked about before? You throw some probability, say an initial state, and it starts to spread out among the other states, and eventually reaches an equilibrium. Well, I want to watch that move around. Think of gallons of water. Move it around in this thing. And finally settle in, so whatever comes into your state is the same amount that you let get out. So what's in there is going to be constant. That's the equilibrium probability. So we're going to use that physical concept to help us solve some complicated Markov chains. Okay, today is Wednesday. We'll see you on Friday. Thank you.